Hi, I'm on. All right, so we're going to talk about the second lesson in differential equations, which is on Euler's method. Euler, Leonard Euler, was basically the goat of mathematicians. Like he had his hand in everything. I mean, other than me, he's the goat. So Leonard Euler, go look him up. I'll have a little blurb about him posted in classrooms. You go learn about this man. He was incredible. If you've studied it, he's had a hand in like coming up with things that we've studied. So you can blame him. All right, we're gonna talk about Euler's method. It's his method. He's a dude. I'm a dude. We're going to learn about it. Okay, so what do you need to know? You need to know what a slope field is. Thank you, Mr. Morris, for teaching us about slope fields. We thank you. And you need to know about local linearity. I'll get into that here in a second and talk about what that all is about. And then we need to talk about proportions, which I think you should know a thing or two about proportions because come on, it's easy. So let's talk about proportions as we get started. We got these two rectangles. What are they? Triangles? They're triangles. Yep, they're triangles. They are similar. We know that because they share an angle down there at A. They both have a right angle. So by AA similarity, they're similar. So all their corresponding pieces will be in a proportion, same ratio. So to calculate the value, we need to be able to set up a proportion. So here we go. The ED is to DA as BC is to BA. There we go. Right. So the length here 5 to the length 12 is the same as Y to 9. So easy to solve that. Bang, bang, boom, cross multiply. We got it. Right. But we got to understand that this old geometry problem is nothing but what happens on the coordinate plane when we talk about slope. We talk about slope as a ratio of rise to run, right? 5 to 12, that's a rise to a run. The slope of the line AE, the line segment AE on that right triangle, and the slope of the line segment AC, they follow along the same line, so they have the same slope. Now, AC is only a proportion of the length of AE. They have the same slope, but the lengths are different. Okay, so that's what Euler's method is going to look at. It's going to look at, okay, well, AC and AE have the same slope, but they don't necessarily have the same length. You can adjust that horizontal distance, and then the vertical distance is going to change correspondingly. So the heart of Euler's method is proportion, because slope is just a ratio, and two ratios set equal, that's a proportion. So we're going to look at this idea of local linearity. The idea of local linearity is this: you take a wiggly curve, and if it's differentiable at that spot, you can zoom in and zoom in and zoom in, and it's a line. Whoa. Wow, that's crazy. It's just a straight line. So at the heart of every curve, or if you zoom in far enough, it's just straight lines, right? So that's where the idea of derivative comes in. This idea of slope of a curve instantaneously is thanks to this phenomenon of local linearity. So here's a little blurb about that. You can read about that in the notes, right? So we're going to build a curve. The idea here is we're going to build a curve by just setting a bunch of little small line segments next to one another, and then we'll zoom out and we'll go, oh, all those little line segments look like a curve when we put them together. Again, so other old problem here. Here's an old derivatives problem. It's already been worked out, so I'll just kind of describe what's going on. We want to use the line tangent to the graph of y equals e to the x at x equals 0 to approximate what e to the 0.1 is. Okay, so this was a problem that you would solve by getting a calculator and getting a value for that. Well, Leonard Euler didn't have that same luxury that you have today. I'm just plugging it into some piece of technology. He had to figure out using this piece of technology Yeah, your brain. You forget about that? Yeah, you forget that you have that at your disposal. So he had to figure out how am I going to estimate these values closely using my brain. So he looked at the graph of e to the x, the red one, classic e to the x, exponential growth. Now the derivative of e to the x is e to the x, okay? So the derivative at 0 is e to the 0, which is just 1. So the slope of the tangent line is 1. Now we need to know what the equation of the tangent line is. Well, the point at x equals 0 is the point 0, 1. The slope is 1. So the tangent line is the blue one there, y equals x plus 1. So you can see if we kind of look at those two lines, the straight one and the curvy one, right? They agree at the point 0, 1. Exactly, right? Without any discrepancy. Now, as the further you get away from that point of tangency, the farther apart those curves seem to get. And if you zoomed out from this picture, yeah, they'd be crazy far away. The further you get away from that point of tangency. So again, Euler is still thinking, well, if I use this tangent line really close to that point of tangency, I can get a really close approximation of my curve just with a straight line, right? I don't even need anything other than a straight line. So you can see the values, f of 0.1. So actually e to the 0.1, that's what you would get if you just cheated and put it in a calculator, or if you use the tangent line, x plus 1, pop in 0.1, and you get approximately 1.1, which is pretty close, right? It's not great, but it's close. And actually, the closer we are to that point of tangency, the better the approximation gets. So if I wanted to do e to the 1 over 100, right, the approximation would be even closer because the two lines are even closer together the closer you get to x equals 0. Now, Euler's method is going to take this idea of lines approximating curves, and it's just going to extend it even further, right? We're going to go even further. We're going to just like kind of repeat this process over and over. We know that tangent line approximations are good approximators of curves, but only close to where the point of tangency is. So we can't go too far away or all bets are off. But if we stay close, then we're okay. All right, now you can see, this is just a preview of coming attractions now. The error between those two curves is huge the further away you get. So, some of you might be thinking, well, what would be better than a tangent line? Maybe a tangent parabola, perhaps, or a tangent cubic function. Is that even possible? Yes, it is. It's called Taylor polynomials. Stay tuned. You're going to love that part. Just wait. All right, we're not there yet. So let me introduce you to what Euler's method is. That kind of primes the pump for what Euler's method is going to be about, things that we already know how to do, and we're just going to spin them in a different way. Right? All new math is just old math repackaged. So Euler's method is just a systematic, recursive way to approximate a curve without really using any calculus. It's really just a numerical way to approximate curves. So we can look at a slope field and we can kind of get the general flow. We can see the current as it flows over the XY plane. Just because humans are good at like seeing big patterns. We can see big general ideas of what's going on. Now, a computer is bad at that, right? A computer doesn't know how to draw a curve. It can draw little straight lines and that look like a curve, but I don't know if they're really, I'm not a computer scientist, so I don't know if that's actually true or not. Can computers draw curves? I don't know. You don't fact check that. I don't know, but a computer can only look at the minute, like the very small part, and only move just a little bit. It can't look big picture. That's all I'm trying to say. Okay, that's all I'm trying to say. We're going to be building curves one step at a time. That's what Euler's method is going to be doing. So a systematic, recursive way to approximate a curve by using straight lines. That's kind of the gist of what Euler's method is about. So let me show you exactly what's going to happen. So here's the steps. It looks kind of ugly, but you're going to see some examples, and you're going to see how easy it actually is. So first thing you're going to do is calculate the width, the change in x, dx. It's back. dx, that width, it's going to be calculated in pretty much the same way. You remember back when we did Riemann sums? I know you do. The dx, that change in x, was calculated by taking the end, subtracting the beginning, and then dividing by how many jumps there were, how many subintervals there were. Remember that? Took b minus a divided by n. Yep, it's the same calculation. The x value at the end minus the x value at the start, divided by how many jumps you want to take. That is how you calculate the value of dx, right? Right? We don't want to go, remember me talking like we don't want to go too far away, right? We want that dx to be small, right? That dx is going to be small. Or we don't have to calculate it at all. The problem is going to tell you what it is. And it's going to be pretty easy to figure that out. So once we have dx, we're going to be able to solve the differential equation for dy simply by multiplying by dx, right? dy divided by dx equals some function. Well, do some quick algebra to that. dy is equal to some function multiplied by the dx. And you'll know the value of dx. So you'll have a function that tells you what the value of dy is. Okay, then we're going to have an initial point. We're going to be adding dx to the x values, and we're going to be adding dy's to the y values, but we're going to have to recalculate that value of dy at each new point. So we're just going to continue that process, add dx, calculate dy, add dy, continue that over till we get as far as we need to go. So here's a little visual of what that looks like. I promise you we're going to get to it eventually. Hold on, hold your socks. Here's a visual of what's happening. So here we have a slope field that's reminiscent of some circles, right? So dy dx is negative x divided by y. And we want to approximate a curve here using Euler's method. So at this initial condition, the start point, we see the slope is positive. We're going to just pick an x. On this, it's going to be called h here, reminiscent of what the limit definition of a derivative was, like limit as h goes to 0. So if we just do this one time, we're going to move over an h, and we're going to move up a distance based on the slope. You see that little red segment right there has a slope that is found by calculating negative x divided by y. And to calculate how far you go up, you just take that slope and you multiply by the h, right? dy is just the slope, negative x over y, multiplied by dx. And then we do it a bunch of times. So after you repeat it, you can see that the distances between each one of those little chunks looks almost like a Riemann sum at this point, right? But it's not. Those little changes in x, those little h's, they're the same dx over and over and over. And you can see how the little line segments are all connecting together, and they form what looks like the top part of a circle, right? So if you do Euler's method a bunch, right, which calculators and computers and programmers like would be able to do this pretty easily because it's a very easy recursive process, we'll be able to come up with a curve without drawing a curve. They would just be drawing little straight lines. And if you make h small enough, you get the actual curve itself, right? So the idea, what you should notice here is that the changes in x, the h values have been shrunk down very, very small. You can actually see that the curve of the circle is a little bit different than what we had in the previous picture. It's actually more of a circle. Now, if you could do Euler's method with dx approaching 0, what do you think would happen? I wonder. All right, so we had some building blocks of what Euler's method is all about: proportions, slope, ratios. We've seen some visuals, we've seen the steps. Let's get to it. Okay, so if we have a differential equation that is given by dy dx is 2x plus y with an initial condition of 1, 3, use Euler's method with 2 steps of equal size to estimate y of 2. So we're on a slope field. You can kind of draw it for yourself, hit the pause button, draw the slope field if you want to. We're at the point 1, 3. So at the point 1, 3, we need to get to the x value of 2. So to calculate dx, we need to take where we want to get to, subtract where we started, 1, and divide by the number of jumps. So we want to get 2, we started at 1, we got to do that in 2 steps. It's not hard to see that each jump would have a size of 1/2. So dx is going to be the same throughout this problem. Dx is 1/2. We're going to be making jumps that are 1/2 to the right each time. Now, we don't know how far we're going to jump up or down with respect to the vertical change. So to calculate the vertical change, we need an equation for dy. dy is the slope equation, 2x plus y, multiplied by the dx, which we calculated to be 1/2. This is pivotal right here. The right equation for dy is pivotal for success here. All right, so dy is the slope, 2x plus y, multiplied by that calculated dx we had before. Now all we're going to do is start calculating. So at the point 1, 3, okay, so the initial condition 1, 3, we're going to calculate what the change in y would be. So we're just going to sub in the pieces that we need. 2 times 1 plus 3 multiplied by 1/2, well, that's 2.5. Okay, and then what are we going to do with that 2.5? We got a number. What do we do with it? All right, so we got to remember we started at a point, we're moving over 1/2, and then we're moving up 5/2. So we're going to move over 1/2. So to the x here in this little table, I use this table, you're going to see it the rest of the way. I'm just going to add the changes in x to the x column, which that's easy because all the changes in x are the same. And then the changes in y's are going to be different at every single level of this table. So I need this third column to calculate dy at each step. So the first dy is 5/2. So I'm going to move to the right 1/2 and move up 5/2. So now I'm at the point 1.5 and 5/2, 5.5. What I mean by that. So 1.5 is the x value and 5.5 is the y value. And then what do? We do it over. Lather, rinse, repeat, right? You read your shampoo bottle at home and it says lather, rinse, repeat. You do it and then you do it again and you keep going. So we're going to do the same exact thing. We know we're going to move 1/2 to the right. We just don't know how far we're going to move in the vertical direction. So to calculate that, we need 2 times the x value plus the y value, that multiplied by the change in x, which we calculated to be 1/2. Well, that turns out to be 7/4. So from that point, we know we're going to move to the right 1/2. We're going to move up 17/4. So we just have to add 17/4 to the y value we were at. And there we go. 11/2 plus 17/4 is 39/4. Yeah. There we go. That's it. That's all we wanted to do, right? We just want to estimate what y of 2 is. There it is. We don't have to do any more Euler's method. There it is. Here's your first Euler's method. It's not that complicated. Well, I mean, says the guy who's done it for a long time. How about we see another one? Let's look at another one. This one's from an actual old AP exam. But don't get scared or freaked out or like excited or anything. It's the same exact process. It's the same exact wording. Here we go. It just is like official AP exam. Consider the differential equation dy dx is y squared multiplied by the quantity 2x plus 2. Let y equals f of x be the particular solution to the differential equation with the initial condition that f of 0 is -1. So just connecting y to f so that when we talk about y and f, we're talking about the same thing. That's kind of all that little part says. So what do we need to know? We need to know what the initial condition is. Okay, that's 0, -1. We need to know what the slope is. We need to know what the differential equation is, which, okay, that's dy dx is y squared times 2x plus 2. Okay, and then we need to know where we want to get. So here in the problem, this is part B. They didn't skip part A. I just deleted it because we didn't want to talk about it. It says use Euler's method. That's code word for use Euler's method. Starting at x equals 0 with 2 steps of equal size, approximate f of 1/2. Okay, that's all we need to know. Starting point, differential equation, what we want to estimate, and now we can make it work. So first thing we need to do is calculate the change in x. So the change in x is where do I want to get minus where did I start, and then divide by the number of jumps. So I want to get to 1/2. I'm starting at x equals 0, and I want to do that in 2 jumps. So obviously each jump is a quarter. So each jump being a quarter, now I need to know what dy is. dy is just going to be the differential equation that was provided multiplied by dx, which we just calculated, by the way. So we know that dy is going to be calculated using the formula y squared multiplied by the quantity 2x plus 2 multiplied by a quarter, which was the dx. So pick it up from the first point. At 0, -1, chuck all that stuff in there. We get that dy is 1/2. All right, what do we do now? Well, we're at the point 0, -1. We're moving 1/4 in the x direction, and we're moving 1/2 in the y direction. So we're going to add those two, add a fourth to 0, add a half to -1, and now we're at the new point, 1/4, -1/2. We're not there yet. We're not at f of 1/2, so we need to keep going. So we just need to calculate dy again. So chuck both of those points into the right places. Chuck the -1/2 in for y, put the 1/4 in for x, calculate that to be 5/32. Okay, well now what? Well, we're going to move 1/4 in the x direction in the positive, and we're going to move up 5/32. So we're just going to add 1/4 to the x column, and we're going to add 5/32 this time to the y column, and we're going to end up at -11/32. What is the approximate for f of 1/2? It's -11/32. Done. Okay, there's Euler's method. All right, so I just want to warn you, don't do this. Okay, slope is a ratio. That means we need to use a proportion to calculate the jumps in y, right? Here's the bogus thinking is by calculating slope, some people think they're calculating the change in y. That is incorrect. If you get the slope is 2, that's the rise over run. That means you're going to rise 2 for every 1 that you move to the right, right? That's what a slope, that's what dy dx equals 2 would mean. You rise 2 for every 1 that you run, right? But what if you only run a third? What does that mean? Well, then you only rise 2/3. That's what it's a proportion, right? So the change in y is a proportion of the slope. It's not the slope, right? You can, if you equate dy and slope, you're doing it wrong. That's bogus thinking. Don't do that. Another thing that you could think bogusly is if you have to work a problem backwards, which might be coming your way. I don't know. Oh, it will for sure. You have to start at the initial condition. Doy, that's why it's called the initial condition. Get it? Initial, that's where it starts, right? Because slope is based on the point, right? If you start at the end point, the slopes won't work out the same way. This is recursive. You got to start at the beginning to get to the end. That's the way recursive things work. You have to start at the beginning in order to get to the end. So start with the initial condition and work forward, no matter what the problem, no matter how the problem is stated. Okay, last example, and then we'll be done. I know you're excited for me to say that. All right, let's keep going. Here's one I just made up. Y is equal to gx. G of x is the specific solution to the differential equation dy over dx equals that mess with an initial condition of g of 2.5 is 1.5. Interesting. Use Euler's method with 3 jumps of equal size to estimate g of 1. Oh, one more jump than the other ones. Okay, here we go. Calculate dx. Well, dx is where we want to get minus where did we start divided by the number of jumps. So I want to get to 1. I started at 2.5. Divide that by 3, and you get that each jump is -1/2. Yes, you can jump backwards. Isn't that fun? Dx is just -1/2. That's all there is to it. So we're going to calculate dy. dy is the slope formula, the quantity x minus y squared, multiplied by the change in x, which is negative 1/2. You can see that here. X minus y squared multiplied by negative 1/2 is how we're going to calculate each dy along the way. So we're starting at the point 5/2, 3/2. We're going to chuck all the appropriate pieces into the right places. 5/2 minus 3/2. The quantity squared multiplied by negative 1/2 is negative 1/2. Okay? So that means we're going to subtract 1/2 from x and subtract 1/2 from y. That's just, okay, weird how it turned out that way. So my new point is 2, 1. Do it again. Plug those in to the right places in our dy calculation, and dy is yet again negative 1/2. So we're going to subtract 1/2 from x like we do with all of these, but we're just going to subtract negative 1/2 from the y. So now we're at the point 3/2, 1/2. We're not there yet. So we're going to do Euler's method yet again. So chuck everything into the right spot. Look at that. dy just so happens to be negative 1/2 yet again. How weird. We got lucky that time. So we're going to add the dx to 3/2 to get x equals 1. We're going to add negative 1/2 to 1/2, and we get that the estimate for this spot g of 1 is 0. Now, is it 0? No, probably not. But that's our Euler's method estimate. Okay, so you've seen 3 examples of Euler's method: moving forward, moving backwards, 2 steps, 3 steps. It doesn't matter how many steps. It could be 45 steps. And it's not going to be, well, 45 steps would be kind of a problem because that's a lot. It's never going to be more than 2 or 3 steps, maybe 4. If you had to do anything more than that, you could totally use some kind of calculator. But this is totally something you should be able to do without a calculator, without taxing your brain too much. It's just a matter of figuring out the process and then repeating that process again and again and again. So again, what have we learned? We've learned that Euler's method recursively builds a curve using little short line segments. We're going to use small equal horizontal jumps, dx, and then we're going to calculate dy by multiplying the slope at that point by the change in x. And we're just going to add dx, add dy as we calculate them along the way. All right, so there's Euler's method. You definitely have to work at it now. You're not a pro like I am. You're not the GOAT like Euler's method or your boy Purvis. But you're gonna get there. You can get up to our level if you just kind of practice. It's really not that hard. It's not like any secret knowledge is happening here. So next time we're going to talk about logistic growth. So that's going to be a couple weeks hence. We're going to talk about logistic growth, talking about like populations don't grow exponentially. They don't. They just don't. They grow logistically. So they're going to like level off after a certain point. You might have studied it in biology. It's called the carrying capacity. I basically said everything I need to say about logistic growth. But stay tuned. The next video is going to talk about logistic growth. I'll see you then. Peace out.